right, section 6.4 is ratios, proportions, and proportional reasoning. And we've hit on this word ratio before. A ratio is a comparison of numbers. Let's look at this. We can write it in three different ways. The most common one for usability is our notation that looks like fraction. So if we have A over B, like this is considered a ratio, but occasionally you will see it written with the dot between them, or you'll see it actually, and we actually read it as A to B. Okay? There are two different kinds of ideas for doing a ratio. One is a part to a whole. So if we had 15 students and 7 of them made an A, we can say that there's a 7 to 15 ratio of A's to the number of students. Okay? But we could also compare a part to a part. So I can consider, for instance, how many students made A's compared to how many students didn't make A's instead of the whole class. And that's considered a part-to-part ratio, and you get something that looks like a 7 and then a colon 8. Okay? Instead of 7 and an over 8 instead of 7 over 15. Just two different ways of understanding ratio depending on what we're talking about. All right, so we're going to give you an example. If the ratio of boys to girls in a class is 2 to 3, 2:3, what is the ratio of boys to all of the students in the class? In other words, we're taking a ratio that is a part-to-part ratio, and we're going to turn it into a part-to-whole ratio. So I'm going to start with writing this as 2 boys to 3 girls. And what I want is I want the number of boys as compared to the whole class. So what would that look like for this fraction? 2 to 5. So we have 2 because that represented sort of the number of boys. It isn't the number of boys, but it's a reduced form of the number of boys. And then on the bottom we have the boys plus the girls, right? So I have 2 plus 3, which is the boys plus girls. So I have a 2 to 5 ratio, or you can read it written like this, would be fine too. Does that make sense? So in example 2, we're going to go the other direction. All right, different problem, different group of students, so it's not the same 2 and 3 as before. But we have a 3/7 of the class are girls. So we've got a part to a whole ratio. And what we want to know is we want to know the ratio of girls to boys on this one. So we can set something up very similar. This is 3 girls compared to 7 in the whole class. Again, that doesn't really mean there's 3 girls and there's 7 people, but somehow it could have reduced to the 3 to 7. So what is the ratio of boys to girls in a class? 3 to 4. And we're getting that because we know that 3 and 4 make up the 7, and 3 represent the number of girls, so we have 4 for the boys. So this would be a 3 to 4 ratio. Or you could write it like this for girls to boys. All right, so a few things about proportions. Proportions are actually a statement that 2 ratios are equal. That's what a proportion is. So we have A over B, we have C over D, 2 different fractions, 2 different ratios, we have equal sign between them, and that is a proportion. And then we have some theorems about proportions that are really handy. And they have to do with sort of reconstructing the way that the proportion is set up to be an equal proportion. So if you'll notice, this first one says that if you have A over B equals C over D, that you can cross multiply. You know that fact, right? You cross multiply and you still have something that's equal on the side. It doesn't leave it in fraction form, but it still is an equal statement. It creates an equal equation, right? What you had originally. The next 2 actually recreate new fractions based on this. So here again, it's A over B equals C over D. And if you compare that to this fraction right here, what is different? What happened? It flipped them, right? So if you take both fractions and you flip them upside down, the equality is the same. Sure, right? I mean, yeah. So in other words, that actually creates another proportion that's equal to the one I started with, but it's in a different order. And you might look at that and say, well, that's very intuitive, and I understand, and I agree with that. This one's a little different. Okay, 622 says if I have that same fraction, A over B equals C over D. What happened here? Yeah, the diagonals, the B equals this one. No, I was right the first time. The B and the C down here, they switched locations, didn't they? Now you might think, well, that seems sort of strange, and we'll do some examples so you can see why that works. But from a very concrete sort of a number perspective of why that works, notice if I were to cross multiply here, I'd still have the same values I do up there, right? And likewise, if I could change this diagonal, could I not also change this diagonal? Sure, doesn't matter which diagonal I'm missing, but I can choose whichever one I want. I can create another proportion that's the same as the one I had. Okay, are you with me? The reason that's valuable is because the type of problems we're working with can be solved in a variety of ways. Your proportions may not look like the ones that I write down, and they may not look like your neighbors, but that doesn't mean they're necessarily incorrect. Okay? They could just be a variation, a different proportion form that follows those different theorems. So let's take a look at the first example. We've got Jim. Jim found out that after working for 9 months, he earned 6 days of vacation time. This is so funny. No offense to you, Grant, because this is how my husband would do this too. See, so I would say at the outset of the job, well, how many days of vacation do I get for the amount of time I have? I would know exactly. Okay, this week's paycheck, I'm getting this week's vacation. It's not what boys do. It's not my husband. He does this. It's just straight out of your book. He comes to a certain time and says, oh, I've got this much vacation. I had no idea how it was screwed. Looks back at me, he's like, oh, okay, here we go. All right, so Jim did this anyway, right? Because I don't know, but in my mind, I think, well, shouldn't Jim have known to begin with? Apparently, this Jim didn't, though. All right, so it says after working 9 months, he's got 6 days of vacation time. How many days per year does he earn at this rate? So the first thing we're going to take a look at is the comparison of things. What are we comparing here? Months work to days of vacation. And so we're going to set it up, and I'm going to do it as a ratio. So we've got his months worked compared to his days of vacation. So when I set up my fractions, I'm going to make sure that I'm always going to put my months on top and my days on bottom, because that's how I've set up the ratio to start with. That's not the only way to set this up. I'll set it up one other way before we're done so you can see, oh, I think I can do it that way, and you can see another option. All right, so if we do this, how many months did he already work? 9 months. And how many days does he have? 6 days. And it will help you, and it will help me if you keep the units on there so you make sure you really put them in the right spot. But the question asks, how many days will he have at the end of a year? Now what?
12 months.
So we need to make sure we change that 1 year into 12 months, because we've got months listed on top for the months worked. And then on bottom, we leave that as days. All right, so we're going to ignore our units now. The units were just for the purpose of helping us set this up. And we're going to do what? We're going to cross multiply, you bet. So I'm going to go with this diagonal first. This is 9x. Then we're going to go with this diagonal, which is 12 times 6. So what is 12 times 6? 72, okay. 9x is 72, then what? So by 9. So what is x? 8 days. Make sense? All right, so here's another thing you could do. Instead of comparing it like this, where we compared the months over the days, you could compare the months on one side and the days of vacation on the other. Okay, on separate sides with an equal sign. So the months would be that he's already worked 9 months and he's received 6 days of vacation. And we know he's going to work for 12 months, because that's what our question's asking us about. And we can set up our X days of vacation down here. And this actually is set up exactly like that last theorem we talked about, where what happened was our diagonal, this diagonal, changed, right? So, and it will work the same if I cross and multiply. It becomes the same 9x equals 72 as the other problem. But it's a different way of thinking about it, and it works just as well. Is that good? Okay. Let's do example 4. On a city map, a rectangular park has a length of 4 inches. If the actual length and width of the park are 500 feet and 300 feet respectively, how wide is the park on the map? So, I read the problem. Well, I have a better idea. Who wants to come and put something on the board for classmates to you? You guys don't get it time. I'm going to pick on somebody else. They're going to volunteer, they're going to volunteer for. I'm going to pick on. Grant! Alright, he's not on his own. You guys have to help him. What should he do?
Length of the map over the length of an actual.
Okay, we could do that. So you've got your map versus your actual values, right?
So 4. And then the actual.
Yeah, would be the 500.
I think the map was the 4.
That's right.
So you can just like length of, and then what will it be? Okay, you got one ratio 4. Now what should this next ratio be?
Length or width of X
Okay. Well, this isn't working. Okay.
You're fine.
Okay.
You can't touch the board.
Okay. Can't touch the board.
You can't touch the board. It's not like chalkboard. Is it length?
Oh, no, it's good. Sorry.
Okay.
I just get to use the eraser to get practice.
That's right.
Width, and we don't know it on the map. Over the 300. Correct?
Yes.
Okay, you can sit down, Grant. Does that look good, everyone? Okay. Who wants to come solve it for us? You're a bunch of chickens, and I know you're not. Because, Rachel, will you come and solve it for us? Sure, you can help in class. Okay, what should you do? Okay, cross multiply, so pick a diagonal. Right, let's write, hey Rachel, let's write the 1200 underneath the 4 times 300. So the other side is the other side of your actual equation. Does that make sense?
Yeah.
Okay. So what goes on the other side of the equation? Looks good. But equals 500x again. What's your next step? Divide by 500. Somebody's going to either do it in her head or her calculator or whatever, so she's not going to hurt. What does she get? Okay, 2.4. So x equals 2.4 inches. And do we need the word inches? Yes, we do. Either the word or the abbreviation. Thank you. That wasn't scary, was it? No, it was fine. Not bad at all. Okay, that one makes sense? All right, this one's a little bit different. I'll do this one to set it up for you anyway. Okay, so we've got Sheila and Dora. Sheila and Dora worked 3.5 hours and 4.5 hours respectively. So that means Sheila worked 3.5, Dora worked 4.5. Okay. They worked on a programming project and they're paid $176 for the project. So some people up in Washington would like you to think that they should split that money equally. I don't think that's such a good plan. One of them work more, right? They should get some more of that money, put more time in. So we're going to do it more equitably, and we're going to split it apart, fair. Just like my kids want, they want it to be fair. So how much should they each earn if they're paid the same rate? Okay, so you have to see what we're comparing. So what are we going to compare to each other? And you have choices. What would you like to compare? Okay, so if we're going to compare the 3.5 and the 4.5, what you're wanting to compare is you're wanting to compare Sheila's hours and money to Dora's hours and money. Does that sound reasonable? Okay. Now, let me just pause for a moment and let you think about there is another way to do that. You could compare Sheila's hours, let's say, to the total number of hours and money. That's the other option. And either one works fine. You're just going to set up the problem a little differently. So Haley told me I'm going to do Sheila compared to Dora. So if I'm going to compare Sheila to Dora, one side of my equation is going to be hours, and the other side of my equation is going to be the money. Does that make sense? Because those are the two different quantities we're talking about here. All right, so Sheila, how many hours did she work? 3.5 hours. How about Dora? 4.5 hours. And while we don't know how much either of them individually made, we do know how much they made combined. Okay? So what I'm going to write down next is I'm going to write down that Sheila made X dollars. So if Sheila made X dollars, how much did Dora make? 76 minus X. Good job. I don't want another variable. Right? I'm not interested in having an X and a Y here. That is not at all what I want. So I can represent it like this. Guys, look outside. It's crazy Oklahoma winter day. All right, so what am I going to do next? Cross multiply. When I cross multiply here, it's going to be a little bit messier than the last ones, right? So let's take a couple steps to write this down. I have 3.5 times 176 minus X. And then I have on the other side 4.5X. What do I do on the left? Distribute. So somebody's going to grab us a calculator so that we're not going to do this out too long by ourselves. What's 3.5 times 176? 616 minus 3.5 X equals 4.5 X. Now what? Add the 3.5 X. So the 616 is on the left. And I have 8X on the right. That's right. Then what? Divide. All right. What is 616 divided by 8? 77. Okay. Now, we aren't quite done because we didn't answer any questions yet. What was the question asked? How much did each earn? So right now, I only have one answer. What part did I answer? Sheila. So I need to specify then which one did what. So Sheila earned $77. How about Dora? 99. And how'd you get 99, Grant?
What did I get to the original?
Yeah, the 176 minus X star, right? Yeah, so we can just take Sheila 77 away from the 176 and 99. Definitely.
When I first read this problem, I got confused when it said Sheila and Dora worked 3.5 hours and 4.5 hours because it didn't specify in my mind which one was.
Okay, so when you see the word respectively, it's going to
In
mean
order.
in order. Yeah, and we use that word sort of as though everybody sort of knows that, and you may not have. Yeah. So whatever the order was of the names is going to be the order of the hours. Your questions?
I thought of just adding the hours together and then figuring out how much, like how many hours divided by the amount.
Like
You could-
176 divided by
Yes.
8, and then just 3.5 times.
But you still have to set these up as proportions. However you're doing it, you're going to do proportional reasoning. So you could do this as Sheila compared to total. And if you did that, you would have Sheila's 3.5 on top and the 8 on bottom. You would have Sheila's X on top and the 176 on bottom. And then you could still do proportions, but from a different perspective, the answers will still be the same. Okay, let's do another one. At Rattlesnake School, the teacher-student ratio is 1 to 30. If the school has 1,200 students, how many additional teachers must be hired to reduce the ratio to 1 to 20? Okay, so this is actually a two-step process. What would I like to know? What am I really asked to find? How many teachers to hire? Well, would it be nice to know to find that?
How many teachers there are?
How many teachers there are in the school. So I'm going to actually first find how many teachers there are in the school. And then, using that information, I'm going to figure out how many teachers I want to have, which will then tell me how many teachers I need to hire. Make sense? Two-part problem, it didn't ask you that though. Right? It didn't say, hey, this is a two-part problem. So you have to deduce that from the information given. So the first ratio, the ratio they're giving you is teachers to students, right? Okay. Somebody's going to come up and do the first half of the problem and find me out how many teachers I have. Don't make me pick. We can get from Haley, thank you. Okay, so what should she write down first? 1 over 30, because that's the ratio we were originally given, right? What's going to go on the other side? Right, x over 1,200, because 1,200 is how many students? Yeah, what? Cross multiply. Alright, so what is that going to give you? So she's got 30x equals 1,200. Good. All right, 40 what? Teachers. So this is what? These are the current teachers in the school. There are currently 40 teachers in the school. All right, so this is what we This is what we have currently. We need another volunteer to find out what we would like to have. All right, Jerry, your turn. Help me out. Okay, so what should she set up if she wants to find out how many teachers we want to have? Over 20 equals what?
X over 12.
Yeah.
X over 1,200. Number of students is still 1,200, right? So we are going to use that 40, we just don't need it yet. Okay, we still want to compare the students to the teachers. We just want the student-teacher ratio to be different than it currently is. All right, so what should she do next? Okay, cross multiplying. So 60 what? Teachers. So we have how many? 40. We want to have how many? 60. So how many do we want to hire? 20. So Charity, you can just write down like a sentence that says we want 20 new hires, or something like that, 20 additional teachers hired. That's what this found for us, right? Thank you. Okay. All right, we have a couple more problems. I'll do these on the board. First, we've got Mary. Mary is working with measurements and writes, I should say writes, the following proportion. 12 inches over 1 foot equals 5 feet over 60 inches. How do you help her?
She needs to know that you either need inches on one side or top or bottom, or you have to change them all to inches. I mean, you don't want to change them all to inches.
Yeah, you didn't want to change them all into inches here.
But you need to make sure the units are the same.
Okay, so we've got an issue with how the units are sort of displayed, right? So Mary needs to have consistency in how she displays her units. Because like right now, I mean 12 inches is equal to 1 foot, so it's reasonable to put those on top of each other. And 5 feet is equal to 60 inches, so it's reasonable to put those on top of each other. The part that's causing problems is right now, she doesn't have always inches on top and feet on bottom or vice versa. She's mixing up that sort of a location of where she's putting things, right? Okay. So she could write 12 inches over 1 foot equals 60 inches over 5 feet, or 1 foot over 12 inches equals 5 feet over 60 inches. So that ordering, that location matters, otherwise things are going to go awry.
Why example 4, like when we did building, did it not matter or cross multiply
It didn't matter because when we divided, we would cancel it out. That's why. And that wasn't the only way, that's how you guys set it up. It's not the only way we could have set it up. Oops, I think it was one more higher, wasn't it? Instead of doing the inches to the feet and inches to feet here too, you could have done like what Kayla was suggesting on this last problem, all the inches on one side. So like the whole map measurement thing over here and the whole actual measurement thing over here. You could have done that. And if you think about it that way, because you want the units to be, then that's fine too. I mean, your inches are the same way. All right, last problem. I sort of hit on this a little bit earlier. Amy's friend told her the ratio of boys to girls in her first grade class is 5 to 6. Amy was very surprised that she would have only 11 students. What can you tell her? Okay, so the ratio doesn't really mean the actual number. Could it be 11 students? Yeah, it could. And some of you are going to be working special ed. That might be a reasonable number. We don't really know a lot about Amy's class, and this is a possibility. But it wouldn't have to be. So what could we tell her? What about that 5 to 6 ratio? word I liked, but I didn't see the word. Reduced was the word I heard, and then I thought it was the word I said. The word reduced is kind of easier. Okay, so the 5 to 6 ratio could, let's say could have been reduced. From the actual number of students. Because 5 over 6 could also equal what? 10 over 12, right? We can multiply both of them by 2. Or, what else maybe? 15 over 18. And we could continue this process with, probably we're looking at one of those two as being more realistic. So if we considered 10 over 12 as our actual count, how many students? If we thought this represented 11 students, the 10 over 12 could have represented 22 students, which would be very realistic, right, for an elementary school classroom around the 20s. If you were looking at a college classroom, 15 over 18 would represent 33 students. That's a very reasonable number for me to teach. And if we were talking about a really large college class, we could make it larger than that. I mean, that would be possible. But those are probably the most realistic ideas here. And this is the issue here.